It's a pleasure for me to introduce Professor Serge Gratton. Since 2019, he has held a chair in the field of machine learning under physical constraints, within which he has developed recurrent neural structures suited to the temporal prediction of trajectories of partially observed chaotic dynamic systems. His involvement in ANITI, which stands for, if I'm correct, Artificial and Natural Intelligence Toulouse Institute, has steadily increased, first as a chairholder, later academic leader, deputy scientific director, and now as the scientific director. And his talk today is titled Multi-Level Physics Informed Methods. So, Professor.
Thank you very much for the nice introduction. I hope that you can see my screen. I will make it full screen. Is that okay for everybody? Can you see my screen?
Yes.
Okay, so let's start. So I changed a little bit the title, maybe to get closer to the topics that have been proposed today, and I stress more robustness and AI for physics. So here are my co-authors. So my PhD student Valentin, someone from École Normale Supérieure de Lyon, Elisa Richetti, and Philippe Touin from the University of Namur. So we are looking for solvers, way to solve problems involving physics, and usually people, when they want to do that, they use classical methods you have certainly heard of, like space discretization, time discretization, finite element, finite differences, many methods like this. And numerical solvers to solve this problem have been developed in the recent years, and there are even recent solvers that are dedicated to some physical applications, and they explore the structure of the problem. So this is the key point in numerical analysis. If you want to get guarantees like accuracy, and if you want to be frugal in your computation, you have to use the structure of your problem. And on the other hand, there is, of course, in this wave of artificial intelligence, has been proposed a structure based on neural networks, and it's called PINS by Reisi and Pandikaris and Karnadakis, and using these techniques that I'm going to describe, you can also approximate the solution of physical problems. Here, I use a partial differential equation.
Sorry, Serge, I interrupt you because we have some troubles to see the full screen. It varies in terms of size, so maybe it's better to have not a full screen but a big picture of your slide. So if you can increase the size of.
Okay, so I will change that. I'm going to share my screen instead. This is what I'm doing now, and also I'm making this. This is what you suggest. Is that better?
Just here we cannot see anything, but
I will. Okay, partager.
Even if you are...
And now you can see.
Yes, it's perfect.
Okay, I'm sorry for this. Okay, so yes, so the idea, as I said, is exploiting the structure of the problems of the problem at hand, and we were talking about the neural network architecture, and in this method, a key ingredient is sampling. So you replace some database that you have usually in problems such as those in image image processing, or in other applications of artificial intelligence. You have a database, and here you build your own database by sampling points in space and time. And for this kind of approach, which I'm going to rely on in the talk, you have many desirable tools such as a convergence theory. So you can prove that if you sample enough, and if you use good tools to approximate your solution, meaning optimization tools, you get you get a solutions, an error that tends to zero when you sample enough. Okay, so just now as a as a summary of all these classical methods, they require precise data. For instance, when you solve a problem from free dynamics, you need to know very well the boundaries of your problem. You also need to know what is if you solve a time-dependent problem, you need to know the initial state very well. Those methods are very they are tuned for a physical problem. You don't reach efficiency if you want to solve all the physical problems. You focus on diffusion, for instance, on some generic equations to get the performance. And those methods, so the classical method, they struggle when you have complex geometries. For instance, you want to simulate what is inside of an engine. So combustion within an engine can be very difficult on the geometry if you want to be very accurate. So the problem has to be discretized very finely, and this is very expensive. On the other hand, so the pins, the AI solutions that I'm working on, they work even with sparse data. They can integrate very easily physical laws in functionally. It's easy to add physical laws. And therefore they can adapt to many physical situations, and it's easy to manage complex geometry. So it seems that there is a clear advantages on the right hand side, and this is just maybe the general properties of the method, and we are going to look more at the performance to see what's really happened with those pins, and you see that the picture is very different when you talk about robustness and accuracy. This is what I'm going to show. So what is pins now? More maybe a closer description of what it is. So what is called here NNWB is a neural network, and a new solution of your problem will be represented as a neural network. So neural network is just a function, and your solution is a function of the space and time variable, and this function will just be approximated by a neural network. So now finding an approximate solution means or reduces to computing the weights and the biases of this neural network in simple implementation. And to do that, you build a loss function, as usually in machine learning, that contains two basic ingredients. On the green side, you have the residual for the equation you want to solve. So you want to minimize this so that your equation is satisfied in the point you sample in the domain. And the blue part of the loss function is what happened on the boundaries, initial state, and so on. So you impose all these conditions by summing them up in a loss function, and you minimize to compute the weights. And when you do that, you have your solution. So it's very the principle is very easy. And but there are some challenges, and for instance, you will see that pins, they can struggle to solve some problems. So it's important to understand when this is happening, and maybe to find solution how to make them faster. So our goal is to address this, and the solution that we will use is the same as what we do for a more standard problem is applying or using the structure of the problem. And here I am talking about the multi-level, multi-level structure of the problem. So what does it mean, a multi-level structure? So multi-level in my case will be a reference to in the first part of my talk to a technique called domain decomposition. And in this technique, to get a faster solver, you use a divide and conquer approach to make your method more parallel and exploit more your computer architecture and be faster in your solution method. And so this is a trend that is followed by many authors, and we are I'm going to show what is the main difficulty with this method, and how you can tackle this difficulty. And there are very nice surveys also on the use of domain decomposition in machine learning. So what is domain decomposition? So the idea is very simple, and it traces back to an idea of Schwartz in the 19th century. And the original idea was how to solve an equation. So you have an equation that is posed on the complex domain, which is a union of the disk and the rectangle that you have on the screen. So this is a complex shape. You see, it's like a keyhole shape, and you want to find the solution for this problem. And the idea of Schwartz is, if I know how to solve it on the disk and how to solve it on the rectangle, maybe I can just iterate. So I solve my problem on the disk. I compute the value inside of the disk, and I use the values that I find on this intersection of the disk and the rectangle to constrain my solution on the rectangle. And again, the solution on the rectangle will be passed to the solver on the disk. Here I will pass the value on this arc of the circle to compute a solution on the disk. And it turns out that you can prove that this alternate solution, disk, rectangle, where you pass the value that are in the intersection, that this method is converging. And it was the way to prove in the 19th century the solution of some equations. Okay, so with pins, how to implement this idea with pins is so you have to computing the solution means computing the weight, so it's training. And the idea would be to split our problem into sub-problems and then use a different pin for each of the sub-problem, and minimize our loss, which has this complex shape here on each of the problem, and use this iteration, pass information from domain to domain, as explained in the Schwartz method. Okay, so I'm not describing the algorithm because it is exactly what I said here. And here it's an example on a simple problem, which is called the Poisson equation. So it's just a Laplace equation. And you see here, this is a plot of the convergence curve. So you measure the error between the exact solution that you get by other means, like a classical solver, and your artificial intelligence method. And you see that when you increase the number of subdomains, so blue is just two subdomains in each directions, and then 3 in each direction, and 4 and 8. So when you divide more the global task into subtasks, you see that the convergence deteriorates. And this is an issue of so-called strong scalability of the Poisson equation. So and due to that, you see that your performance of your pin will be very low if you decide to split your problem. And you see that the accuracy is not very good. Even with the blue method, you have an accuracy of 10 to minus 3. With a traditional solver, you would have 10 to minus 8. So a first message is pins are not so good if you use it out of the box for accuracy. So how to do that? So what is the problem? Is that you have only communication between neighboring subdomains, because you pass information from domain to domain, and a mechanism is lacking that would enable an instant transmission of information all across the domain. And so we need to implement such a mechanism if we don't want to see this behavior. So and this is just because you split into subdomains and just they talk locally, and it's very slow to make a global convergence when the discussion occurs only between neighbors. So you need this global communication schemes to occur, and this is what we implemented in this algorithm. So this is the core solution, which is based on value that we compute on the fine on the fine solution. So we transmit information from the fine solution to the coarse that will serve as constraint, and then we solve we compute a core solution, so a solution which is not as accurate, but it will be on the whole domain, and again transmit this to the fine domain. And so this core solution is just a way to transmit quickly information between local domain in a very efficient and very quick way. So when I say transmit information, it's always a combination. So in those methods, you implement strategies like this one, where you make linear combination between the current course information and the fine information. So you try to balance how much you inherited from the fine solution and the global solution. And in fact, the information is exchanged just by the tools that you have to solve for the pin, which is a loss function of your artificial intelligence problem. So now, what is the performance of that? So this is again a Laplace equation with a known solution, and here W1 and W2 are coefficient in this sign. And when the 1W is high, you introduce high frequencies in your solution. So here I have W4, W2 equal 4. Here I have W2 equal 3, and you see the difference in the solution. So what happens here is you see that for this case, the thick convergence curves are the one with the coarse problem that is ensuring a quick coordination of all the local solvers, and you see that all the thick curves, they converge very quickly and at the same rate. So we manage to balance and to solve this issue of many subdomains that do not communicate at a fast enough pace by using this global mechanism. And you see that now for all the discretization, we get a very good convergence, and it is similar. So it means that you can really split your problem into sub-problems that will be easier to solve and benefit from that in a parallel setting. So this is the so-called strong scalability. However, when you increase the W2 here, so the frequency content, it does not work. This cooperation is not working. So you see here that now the thick curves are not very good. So again, we get this lack of robustness of the pins when of physically informed neural network when the frequency is very high. So the idea to solve this is to vary some hyperparameters. So if you increase the number of outer loop if you increase the number of epochs, you can get a smooth convergence curve. Is the one that you have here in violet, and okay, it works, but it costs really a lot because you have to increase a lot your iteration. So what is very interesting here is that due to the structure of the program, you can understand where this comes from, because now you introduce a mechanism to exchange information quickly, and still it does not work. And this is due to a genuine property of the pins, is that they don't solve very well for high frequencies, and this is the so-called F principle. And if you look at the error that is obtained when you have problems with several peaks, you see that you at the beginning you converge only for the few first epoch on the for the low frequency between 0.2 and 0.4, and to get high frequency you need a lot of iterations. So this is exactly what you observe here. We needed a lot of iterations. So the problem is that now it makes the method very expensive. And is it possible to get rid of that? Against the idea would be to tackle directly the issue of multiple frequencies, and to do that we introduce a technique where we compute our solution as a sum. So here, just for the purpose of the presentation, I introduce a sum of two terms. One is low frequency, one is high frequency, and I introduce dedicated network to tackle all the different frequency components, and I solve iteratively for the first one x2 and then for x1 alternatively for each of the frequency. So this would be a possible algorithm to do that. So it's just a selection of the subproblem to solve, find our course course grid, find frequency or high frequency, and then we solve the problem and iterate. And so if you do that with this test problem, you again, we have parameters to introduce high frequencies, and we choose several networks. So I'm not entering into details for all the network size, but the idea is that for all these network size, the price is the same for a given number of outer iterations. And here we see what is happening with now this with this kind of problem. You see that you get a good convergence with beta is small, but when beta is large, only the curve FAML is so the curve in violet is converging very well. And to achieve this, we added what I told about tackling directly the high frequencies. And to do that, we implement a radial scaling of all our data to implement a form of zoom, and we use a wavelength inspired activation function. And with these tools and a representation of the solution on the Fourier space, we are able to obtain this very quick conversion curve in violet. So here is the solution method, the problems that we encounter with pins, and how we solve it. Our architecture is here all the frequencies, and we iterate across all the frequencies, and we introduce these lambda parameters to implement the scaling, the zooming to tackle the various frequencies. There are more test cases. I'm not going to enter into details. More test cases and architectures. And the result now, when we use this FAML method, so the MSC in this column here, you see that you get a very stable performance for all our problems, and it performs very well now, even with high frequencies. So the conclusion is that it's not so, even if in principle pins are very appealing, it turns out that using them, so solving problem with physics using artificial intelligence is not very easy. And it turns out that you have a lot of questions of robustness that have been tackled with existing solvers. And we demonstrated here how to exploit the knowledge that you have from the physics to design a robust solver. And of course, with this kind of solvers, we can tackle some questions on explainability because we have an underlying physics, so we can better understand why there is why such decision is taken by the network. But we need also to understand how the network converges, and this spectral bias and the importance of the frequency here in the solution of pins is really crucial. So for us, and maybe I heard the name today, hybrid AI is really something that is very important. Being able to combine knowledge from different domains and not rely only on data and loss to minimize. Of course, when the problem involves physics, you have a lot of tools just that come from the different phenomena that you are considering in the problem, and also all the knowledge you have on this phenomena. So thank you very much for your attention, and of course I am at your disposal for questions. Thank you. So, yes,
Yes.
I hope I was not too long.
Yeah, we have two questions on the chat.
Yes.
Well, some more now. I'll go one by one. Maybe we don't have time for all of them, but well, the first one is regarding what you mentioned at the end about explainability and pins. So the question is regarding the different techniques that may be used for explainability in pins. Which kind of techniques could be applied for this?
Yeah. So the question occurs quite often in problem involving physics. We know that many things happen when you use a black box. It's the same in meteorology and in all these applications that are critical systems. And for this, we in pins you have access to all the items you want to minimize in the loss function, and you have an interpretation, a physical interpretation of that. So, for instance, when a decision, you have diagnostics on the scale that you reach in your solution that is based here on the Fourier analysis, but you can also assess how much you were able to satisfy the boundary conditions, how much you are able to satisfy some balances that are in your physical problem. So if something, you can diagnose how much you were able to take into account all the information that you have from the physics, and this is in case, and then you are back to the usual problem, where you have some laws that are governing your systems, and you can check which one are satisfied. The only critical point is training, because you have all these equations, but you have the training process that is quite often suboptimal, and you have to understand what happens in this optimization problem, because everybody assume here that you are able to find the global minimum, and our study here is shedding some light on how convergence occur, in which order you get the frequencies, and so you may get a wrong solution a representation of the physics that is not satisfactory, not because your equation were not of a good quality, but just because the solver did not converge. And for that, you have to analyze the error in the good old way using expansion in Fourier basis or in the adaptive basis and see what's happening.